Welcome to the first video on sum and difference formulas. And we are going to be focusing specifically on sine and cosine difference formulas. And here's the reason that these identities even exist. They allow us to use the unit circle to find an exact value of trig functions at other angles that are not on the unit circle. So for instance, if we looked here first, if I wanted to find the sine of 75 degrees, if I didn't want to pull out my calculator and use a decimal and I wanted an exact fractional answer, we could think of 75 degrees as either an addition or subtraction fact of things we already know. So instead of writing sine of 75 degrees, we could write sine of 30 degrees plus 45 degrees. Or we could even write that sine of 75 degrees is the same as sine of 135 degrees, which is on the unit circle, minus 60 degrees, which is on the unit circle. So we could use things we know to find things we don't know or not are on the unit circle. Now, here's something that I do want to make clear, at least with the calculator. I want to let you know that these two things are definitely not the same. You can't distribute the sine in to the 30 and the 45 because sine is a function. It's not a variable that we're distributing. But let me prove it to you. If I wanted to find the sine of 30 plus 45, as you know, that's the same as sine of 75 degrees, which if I plug that into my calculator, would be 0.965, about 0.965. If I incorrectly distributed the sine and I plugged these into my calculator, sine of 30 is 1/2 or 0.5. Sine of 45 degrees is 0.707. If I add 0.5 plus 0.707, I get that to be 1.207, which is definitely not equal to 0.965. So I would write yourself a note. You cannot distribute a trig function. So this one is what we're going to be using today, that logic, but this one is technically mathematically illegal. So here are the sum and difference formulas. As I said before, the sine of a plus b as an angle does not equal the sine of a plus sine of b. This is incorrect. Instead, mathematicians have proven that sine of a plus b does equal something in particular. It equals the sine of a times the cosine of b. And how I actually view it is that if you keep these things in the same order, it makes more sense. It equals the sine of a times cosine of b plus the sine of the opposite angle then the cosine of the opposite angle. So if you take the sine of one angle, next you take the sine of the second angle. If you take the cosine of the second angle, next you take the cosine of the same angle or the first angle. And I want you to notice, for sine, if the sine is originally plus, it stays plus. If the sine is originally subtracting, it stays subtraction. That is because if you think about transformations from unit 2, whenever you had a y value, it did exactly what you expected. However, if you take a look at cosine, the sum and difference formulas, cosine, notice that cosine repeats twice and then sine. That's a good way to remember it because cosine has to come first because of this cosine. Notice though that if I start with an addition, it ends up being subtraction here. And if I start with a subtraction, it ends up becoming addition. That is because if you think about transformations again, x always does the opposite of what you expect. That's at least a memory trick I use based on things you already know. Now, these formulas are proven using something called the law of cosines, and that comes in Unit 6. So if you wouldn't mind for now, this is a diagram that we do use to prove it, but I'm going to wait to prove these to you until after you've learned the law of cosines. For now, if you could just accept that these formulas are true, we're going to use them correctly, and then I will prove it to you later. So here is one way that we are going to use these formulas. One thing I'd like you to do is if I give you a problem like this, I want you to recognize this is a sum or a difference formula. And I have them here just for another reference. So which one of these is true based on what I gave you. Sine of an angle, cosine of an angle, minus cosine, sine. Well, I'm looking for sine of an angle, cosine of an angle, so it's going to be one of these two, minus. So my eye goes here. So I have sine of 165 degrees, cosine of 45, minus cosine of 165, sine of 45. So what I could do is go backwards and rewrite this more simply as the sine of the first angle A minus the second angle B. If I simplify that, sine of 165 minus 45 is really the sine of 120 degrees. And if I bring back my unit circle here, if I paste that in, the sine or the y value at 120 degrees is really, so 120 degrees is really here. So the sine of that value is really the square root of 3 over 2 because we're dealing with the y value. So the goal of these problems, if possible, is to get a single answer because we're using the unit circle. If we look at the second problem, we're dealing with cosine, cosine minus sine, sine. If I look at my sum and difference formulas, this is the one that catches my eye because I have cosine, cosine minus sine, sine, which means that this could be rewritten as a single trig function, cosine of the angle plus the other angle, or 20 plus 40, because those are the two angles that I'm using. So it's really the cosine of 60 degrees. And so what is the x value at 60 degrees? Well, it looks like it is a positive 1/2. Let's do the same process, but this time give it in radians. Let me show you it's the same idea. Cosine, cosine minus sine, sine. Again, it's this formula. So it's going to be rewritten more simply as cosine of the first angle, pi over 12, plus the second angle, 5 pi over 12. Luckily for us, same denominator. This is really 6 pi over 12, which reduces to pi over 2. What is the x value at pi over 2? Why, that's 0. Number 4, sine cosine plus cosine sine. This first one is what we're going to be using, and we're going to change it back to or condense it to sine of a plus b. So it would be sine of 4 pi over 9 plus pi over 8. Now this time I do need a common denominator. The common denominator is going to be 72. So I'd multiply this one by 9 over 9. I multiply this one by 8 over 8. So I'd get sine of 32 pi over 72 plus 9 pi over 72. So that would be sine of 41 pi over 72. Now, is 41 pi over 72 on my unit circle? No, it's not. So in my opinion, you would leave the answer just like this because you want an exact answer. And if you plug that in the calculator, you get a decimal. So let's leave it like that. So option 1 for this section, go backwards and condense. Another option for this section is if I give you the original, we need to use these formulas to expand it and actually calculate it out. The reason we need to do that is because 105 is not on the unit circle. So we need to rewrite this problem as cosine of either something plus something or something minus something using values that are already on our unit circle. Speaking of that, here's a version of the unit circle I'll paste in with all the angles in degrees. So let's think about this. How can I rewrite 105 based on things I already know? We could do cosine of 45 degrees plus 60 degrees, because those are both in the unit circle. We could do cosine of 135 degrees minus 30 degrees. We could do the cosine of 330 degrees minus 225 degrees. So as you can see, there's probably a lot more options we could use from here. A lot of you on your own might have thought of 45 plus 60. So this is really tempting to use. But for the sake of this video, I'm going to use the second one because there's a couple things I want to point out with it. And so if I want to do cosine of 135 minus another angle, I'm going to be using this formula because we're doing cosine of an angle minus an angle. So what we need to do is rewrite this one or expand it. Cosine of 135 degrees times the cosine of 30 degrees plus the sine of 135 degrees and the sine of 30 degrees. And the good news is that we can use our unit circle now. The cosine, or the x value at 135 degrees, is negative root 2 over 2. And we're going to multiply that by the x value at 30 degrees, which is root 3 over 2, plus the sine, or the y value at 135, is root 2 over 2, positive. Sine of 30 degrees is 1/2. So notice we're getting exact values from the unit circle. If we multiply these, we would get negative root 6 over 4 plus root 2 times 1 is root 2 over 4. If we combine this to be one fraction, as a common denominator, we could write it as negative root 6 plus root 2 over 4. These are not like terms. They do not have the same radicand. We could even change the order and write the root 2 first, subtract the root 6, and then divide it by 4. Either one of these answers is awesome. So the goal is to use the unit circle with angles that we know, use the sum or difference formula based on if you decided on a sum or a difference, and then use the unit circle for the exact values to figure out an exact answer. We are going to do one more problem together here, and this time we're going to do sine. Now, sometimes you're going to be given angles that are in radians. As a suggestion, because there's already so much going on in this video, is I would suggest doing something from unit 3 and multiplying by 180 over pi to change this into degrees to make your life easier. So if you do that, the pi's would cross out, and then we can cross cancel as well. We can think about how many times does 12 go into 180. It goes in 15 times, so this reduces to 15 and 1. So if I did 19 times 15, that would get me 285 degrees. So think of this problem instead as the sine of 285 degrees. So what I'd like you to do, and let me again paste the unit circle in here. Okay, I'll bring that over here. Look at the angles that you have and see if you can figure out if you can either add any of the two angles or subtract any of the two angles to get 285. So please pause now. Okay, so over here in blue, here are some options I found. If you found one of these, that's wonderful. All of these values are on the unit circle, and you have some additions that get to 285 and some subtractions that get to 285. Because the last example, I ended up choosing cosine of a subtraction, this time I will choose sine of an addition. So I'll just go with the first one, but any of these would get the same answer. So if I used sine of 240 degrees plus 45 degrees, I would use this first expansion idea. So it would be sine of 240 times the cosine of 45 plus, again, you don't need to follow this exactly. We did sine of 240 the first time, so it would be sine of the other angle the second time. And the same goes with cosine. We did cosine of 45 the first time, so it's cosine of 240 the second time. So let's use our unit circle. 240 degrees is here. The y value at 240 is negative root 3 over 2. The x value, or the cosine value of 45, is root 2 over 2, plus sine of 45, or the y value, is root 2 over 2, and cosine of 240 is negative 1/2. So that is really similar to the last problem. Negative root 3 times root 2 is negative root 6 over 4, plus negative root 2 over 4. So this time both of them are negative, so if I combine them into a single fraction, the denominator would be 4, and we could just keep it as negative root 6 minus root 2. And that would be my answer in exact form. So whenever you do sine and cosine, you're going to end up with values that look like this because you generally are dealing with 1/2s and root 2 over 2s and root 3 over 2s. So you're generally going to have a denominator of 4. Feel free to try this on your own before class.